Welcome back to the next session of electrostatic potential and capacitance. Friends, in the previous videos, we discussed about the potential energy of a single charge and the potential energy of a system of two charges in an external electric field. Today, we are going to discuss the potential energy of an electric dipole in an external electric field. Just as a reminder, as I said in the previous video, we have to place a source charge somewhere and it is producing the electric field, and that electric field is passing through this board, and the entire board itself is considered as an external field. In that external field, I have drawn field like this in this region. So now, if I place an electric dipole in an electric field, what happens? That I have to discuss, and how much energy or potential energy is stored in the system or in the dipole, that I have to calculate. So before calculating, let us discuss some more important points which we have studied already in the chapter 1 as well as chapter 2. What is electric dipole? Dipole is a system of two charges separated by a small distance 2a, or else you can write, consider an electric dipole placed in consider electric dipole consisting of two equal and opposite charges separated by a small distance 2a. Then the dipole moment P is equal to 2a into q into p cap. Say equation number 1. This we already know in the previous discussion. After this, after writing this part, again continue. Let theta be the angle subtracted by the dipole axis or the dipole moment with respect to the electric field vector E. Afterwards, we already know that if a dipole placed in an uniform electric field, the net force on the dipole is 0, but it experiences the torque, and that torque is given by the already derived tau is equal to P cross E. That we have to derive, or if I write in a mathematical form, tau is equal to P into E into sin theta. Say equation number 2. Afterwards, as I said, if two forces are there, look at this. This is the direction of the one force, and this is the opposite direction of the force. If it is placed in the uniform electric field, it starts rotating. That is called as torque or dipole, and that all is given by tau is equal to Pe sin theta. When the torque is rotating in an external electric field, then the electric field wants to nullify the rotation of the dipole in order to restore the original position. Suppose if I place the dipole with an angle of say theta 1, then if it is unstable, suddenly what happened? The dipole, the external electric field exerts a force or rotates the dipole so it comes back to the rest position like this. Now it is stable dipole. So now at that time, the external electric field rotates the dipole at a small angle of d theta. That means instead of the previous angle, it changes. The external electric field exerts torque on the dipole and it rotates with a small angle, say d theta. At that time, a small work is done, and that small work done is given by dw is equal to tau into d theta. It's very, very important equation number, say 3. So now we arrived at a small work done equation, that is dw is equal to tau into d theta. Then if I just rearrange this term, then I get dw is equal to tau means what? Pe sin theta. P into E into sin theta into d theta. This is equation number 3. Now I want to calculate what is the total potential energy stored or acquired by the dipole when it is placed in an external electric field. So if I want to calculate, then I have to integrate. That means small work done are many small work done with D1, dW1, dW2, dW3, so on. Then I have to add all the small work done to calculate the total potential energy or total work done. For that, I have to integrate between the limits theta 1 to theta 2. Integrate equation 3 between the limits theta 1 to theta 2. Then W2 is equal to theta 1 to theta 2. Then it is dW. Afterwards, if I write this, then theta 1, theta 2. What is dW here? dW is PE sin theta d theta. PE sin theta into d theta. What is the variable here? D theta is a variable. What is variable function is associated with the sin? Only means we have to retain the sin theta inside a integration term. T and E are constant term. Take it outside. So if I take it outside, then W is equal to P into E between the limits theta 1 to theta 2. Then it becomes sin theta. Then sin theta into d theta. Then if I integrate, then this becomes P into E into differentiation. Integration of sin theta is minus cos theta between the limits theta 1 to theta 2. Then if I substitute the terms, then upper limit and lower limit, I get W is equal to P into E minus cos uppercase minus lowercase. So this becomes minus cos theta 2 minus of minus becomes plus cos theta 1. So you can write minus of minus becomes plus. So I write plus cos theta 1. Then if I rearrange this equation, I get W is equal to P into E into cos theta 1 minus cos theta 2. It's one. Very important equation number 4. Now let's come to the point. One more important thing is, so now here I place the dipole at a distance of now in the external electric field vector E like this. Then the dipole has subtends an angle theta with respect to the direction of the electric field. So this is the direction of the electric field, and this is the direction of the is like this. This is like this. It subtends an angle theta here. Now suppose instead of this, at the beginning only, that means theta 1 is my choice, theta 2 is the electric field choice. So it will acts on the dipole to make it stable, the dipole in an external electric field. So what I have to do is, so theta 1 is my deciding factor. What I will do, I will place exactly perpendicular to the direction of the electric field. How? Like this. So this is the direction of the electric field, this is the direction of the dipole moment. Then theta becomes how much? 90 degree. Suppose if theta 1 is equal to 90 degree or say pi by 2. If theta 1 is equal to pi by 2, obviously theta 2, it may be greater than 90 degree or it may be less than it. We don't know because it is depending on the direction of the electric field and the strength of the electric field. So what I will do, then theta 2, I just imagine myself, say now it is theta, simply say theta. Then if I substitute these terms in the above equation, what happens? So this potential is nothing but what U or work done, both are same. So if I write like this, then U is equal to W is equal to, then you substitute this, you get PE into cos theta 1 90 degree cos pi by 2 minus cos theta 2 is what? Simply theta, substitute. So cos 90 we are aware of that is 0. So it becomes 0, then it becomes minus simply U is equal to minus PE cos theta. PE cos theta is the potential that is stored in an electric field. Then look at this, two vector quantities are there, they are associated with the cos theta. If they are associated with cos theta, what I have to write? I have to use the dot product. So then U is equal to minus vector P dot vector E. So this one more expression. So U equal to minus P cos theta, U equal to minus P dot E. Both are third square for the equation, that is potential energy of a dipole in an external electric field. So this is one more derivation related to the potential energy in an external electric field.